6 problems from the Spring 2024 Calculus 3 exam, number 2. Let's do this. Find and classify the two critical points of the function f of xy equals x cubed plus 6xy plus y cubed. Okay, now remember, we got to know what kind of problem we're doing. And there's kind of a big clue. It tells us, right? It's a find and classify critical points problem. Now that means we're going to take the gradient, set it equal to 0, and classification means second partials test. So let's start with finding mean. So we're going to set our gradient equals 0. Now that means we really have two equations. Our f sub x, that's going to be 3x squared plus 6y. Set that to 0. Our f sub y, well, that'll be 6x plus 3y squared. Set that equal to 0. All right, two equations, two unknowns. We need to solve for x and y. And, okay, what can we do? Well, one thing we can certainly try is substitution. Because what do we have here? For instance, notice we can solve for one of the variables. It doesn't really matter which one we solve for. Let's suppose we solve for x. And, well, we can solve for x here. X equals, and move the 3y squared across, divide by 6, minus 1/2 y squared. Okay, plug in. And what will we have? Well, we're going to get 3 times minus 1/2 y squared plus 6y equals 0. All right, well, let's, oh, whoops, I put y squared. It's x squared, right? So it's y squared squared. Okay, good. Pay attention, right? It's good to pay attention. So that would become, when we clean that up, 3 over 4 y to the 4th plus 6y equals 0. You can pull out a 3/4, and you can pull out a y because both terms have a y. So, okay, so that becomes 3/4 y times y cubed. Now, when you pull out 3/4 out of 6, to pull a 3/4 out is the same as to multiply by a 4/3. 6 times 4/3, 24 over 3, also known as 8. So, you get y cubed plus 8 equals 0. Now that leads you to two possibilities. Y equals 0 or y cubed plus 8 equals 0. Now y equals 0, easy to solve for y, 0. X is minus 1/2 y squared, so x equals 0, and that gives us a point, 0, 0. Now how about here? Y cubed plus 8. Well, that's y cubed is negative 8. We can take the cubed root. Now cubed roots don't have the square root issue. Square roots we'd have a plus minus, cubed roots we don't. And the cubed root of a negative number is negative. In this case, it's negative 2. What's x? Well, square your y value. So negative 2 squared is 4, times by negative 1/2, x equals negative 2. So you get the point negative 2, negative 2. Okay, so now we have found our 2 points. And we knew we were going to find 2 points because they told us 2 points. So we're halfway done. Woohoo! But we have half to go. So let's go into phase 2. Now for phase 2, what are we going to look at? We're in the classify. Classify means second partials test. So the only way to classify critical points is second partials test. So remember, that means we're going to do the following computation. We're going to look at fxx, fyy, minus fxy quantity squared. All right, so we need to compute these derivatives. fxx, that would be 6x. fyy, that would be 6y. How about fxy? Well, that would be 6. All right, lots of 6's here. So we get for our discriminant, our d, 6x times 6y minus 6 squared. Or if you like, that's 36xy minus 36. So it's 36 times xy minus 1. All right, so let's plug in. At 0, 0, d is 36. 0 times 0 is 0 minus 1. Is times minus 1 is negative 36, which is less than 0. D being less than 0 tells us saddle, right? Let's just write this down for reference. So this is not part of the problem, but d less than 0, saddle. D greater than 0, we split. If fxx less than 0, then that's a max. Fxx greater than 0, that's a min. And if d equals 0, we don't know. We don't have the tools. Okay, so we got negative. That's how we knew saddle. At this other point, negative 2, negative 2, because that was our other point, we're going to get d is equal to 36 times, well, negative 2 times negative 2 is 4 minus 1 times 3. It's 108, but all we care about is that it's positive. Okay, positive means we're one of them. But which one? Well, we see that fxx is negative 12. It's also, by the way, the same as fyy. They're both negative values. Since they're both negative, well, that means that we are in our max. And second partials test, by the way, there's that little set of 3 faces. So negative means we're max. Okay, so that says, okay, so we didn't write this down. This is saddle. And so this is a local max. And now we'll just summarize. So our critical points, we have 0, 0 is a saddle. And negative 2, negative 2 is a local max. And we'll box it so the grader can easily find it, give us all the points that we want, all the points that we deserve. On to number 2. Compute the gradient of f of xy equals cosine pi x plus x squared y plus e to the xz minus yz. So remember, gradient is just another way of saying, let's find all these partial derivatives. Okay, so the gradient, that's our notation, gradient f xyz is slot 1. Take the derivative with respect to x. Derivative of cosine, negative sign. Make sure you have that pi accounted for. So minus pi sine pi x. Derivative of x squared y with respect to x, 2xy. Derivative of e to the xz will be z e to the xz, because we're treating y and z's like constant. That won't be anything. Comma. Now take derivative with respect to y. 0 x squared 0 minus z. Now take derivative with respect to z. 0, 0 x e to the xz and minus y. And there's our gradient. Okay, that's part A. Part B. Wow, and notice this is 6 points. We already got most of the points. Oh, this is a great problem. Okay, use the gradient of f in part A to find parametric equations for the normal line to the surface described by the equation f of xyz equals 0 at the point 0, 1, 2. All right, so we're looking for parametric equations for the normal line. Now, how do you find lines? Lines, you need 2 things. You need a point and a direction. Well, good news, we're halfway there without doing anything because they gave us a point. Okay, so here's our point. Now, where's the direction going to come from? We're going to use part A. So the direction is going to come from the gradient, because the gradient has this sort of built-in notion of perpendicularness involved. Okay, so for us, we are going to plug in. Now, everywhere where you see an x, you put a 0. Where you see a y, you put a 1. Where you see a z, you put a 2. Okay, so sine of pi times 0. Sine is 0, gone. 2 times x, 0, gone. z e to the 0. Okay, that's going to have something. So that's going to be 2 e to the 0. That leaves us with a 2, comma. 0 minus 2, comma. 0, that's going to be gone, minus 1. Okay, so 2 minus 2 minus 1. All right, so that's our direction. Now, remember when we're making lines, it looks like the following. We have x equals y equals z equals, and then in the first slot is your point, and then plus. The second slot is your direction. So for us, our point is 0, 1, 2. Our direction is 2, minus 2, minus 1. Or if we just write that a little bit better, clean it up, we get x equals 2t, y equals 1 minus 2t, z equals 2 minus t. And we're done with part B. Part C. Use the gradient of f in A to find an equation for the tangent plane to the surface described by the equation f of x, y, z equals 0 at the point 0, 1, 2. Notice it's the same point. Now, what do you need to make a plane? You need a point. We have a point. And you need a normal. Where's the normal going to come from? Well, surprise! Not really. It's going to come from the gradient. So, we already did the work. It's 2 minus 2 minus 1. So, there's our normal, just copying. And so we get, those are our coefficients, 2x minus 2y minus e equals something. What goes here? What's in the box? Well, that's when you use your point. You have 2 times 0 minus 2 times 1 minus 2. Well, that's 0 minus 2 minus 2. That's minus 4. That's what goes there. So we have 2x minus 2y minus e is minus 4. There's our plane. Number 2 is done. On to number 3. Consider the function f of xy is 1 plus 2x times sine y plus cosine y minus 3x squared. Okay, part A. Find the first order Taylor polynomial of f of xy centered at 0, 0. Okay, so if we're doing first order Taylor polynomial, we need to know a couple things. And by the way, first order Taylor polynomial, this is just another way of saying tangent plane. So if you're not like, what is that? Oh, tangent plane? Yeah, we can do that. What do we need? We need to know f of 0, 0. And so we're making a list here. We need to know f of 0, 0, fx at 0, 0, fy at 0, 0. And in particular, our first order Taylor polynomial would be, I'll write out sort of long form, f0, 0 plus fx 0, 0 times x minus 0 plus fy at 0, 0 times y minus 0. So once we have those numbers, we're good to go. Now f at 0, 0, we can just plug that in. We'd have 1 plus 0, then we'd have sine 0 plus cosine 0, which is 0 plus 1, then we have minus 3 times 0 squared. So that's 1 times 1 minus 0. So f of 0, 0 is 1. We need to find our partial derivatives. fx of xy, well, derivative with respect to x, so the y's are like constants. So you'd have 2 times sine y plus cosine y minus 6x. fy xy, well, that's 1 plus 2x is a constant. Then the derivative of sine y is cosine y. Derivative of cosine y is negative sine y. So cosine y minus sine y. And then the minus 3x squared goes away. Okay, so evaluating fx at 0, 0, we'll get 2. 0 plus 1 makes 1, so 2 times 1 minus 0. So we get 2. Fy at 0, 0. We'll get 1 plus 0, which is 1. And then 1 minus 0. And, all right, that's also 1. 1 times 1, 1. So that's a 2. That's a 1. And so our answer, what's our first order Taylor polynomial, is we get 1 plus 2x plus y. And there we go. That's our first order Taylor polynomial. All right, great, great, good. Now that's part A. Part B, second order Taylor polynomial. Okay, so what's going to happen for second order Taylor polynomial, you're going to have the first order terms, which we already have, but then you're going to add some new terms. You get your fxx at 0, 0 times x minus 0 squared times a half, so divided by 2, plus fxy at 0, 0, x minus 0, y minus 0, plus fyy at 0, 0 times y minus 0 squared, again divided by 2. So we have to find these derivatives and plug in. Okay, so we have 3 second order derivatives we have to find. fxx. All right, well, that doesn't have any x's, so we have a negative 6. fxy. All right, that minus 6x is going to go away, so we have 2. Derivative of sine is cosine y. Derivative of cosine is negative sine y. And then fyy, well, what will that be? Well, 1 plus 2x is a constant. And then derivative of cosine is negative sine. Derivative of negative cosine is negative. Derivative of cosine is negative sine. Derivative of negative sine is negative cosine. Okay, so at 0, 0, we get fxx is negative 6. fxy at 0, 0, we get 2 times 1 minus 0, so that would be a 2. And, all right, and then we have fyy at 0, 0. Well, we have a 1, and here we have a minus 0 and a minus 1, so that's a negative 1. So, what do we have? Well, we have our first order, which we already found in part A. So 1 plus 2x plus y. fxx of 0 over 2. So minus 3x squared. fxy. So plus 2xy. And then fyy divided by 2 would be minus 1/2 y squared. Okay, so there's our second order Taylor polynomial centered at 0, 0. Now, part C. Use your result in part B to approximate f of 0.1 comma negative 0.2. Your final answer should be a 2-digit decimal value. No rounding, please, or a fully reduced fraction. Okay, so we're just going to plug in, because what's the idea? Well, the idea is that f of xy is approximately 1 plus 2x plus y minus 3x squared plus 2xy minus 1/2 y squared. So we're just going to plug in. In this case, we say f of 0.1 comma negative 0.2. Well, that's about 1 plus 2 times 0.1. Okay, so that's going to become 0.2 in a second. And then plus y, which is a negative 0.2, minus 3 times 0.1 squared plus 2 times 0.1 minus 0.2, and then minus 1/2 0.2 squared. Now, here you have a positive 0.2 and a negative 0.2. Those actually cancel. That's cool. Here you have a 0.1 times a 0.1, which is a 0.01 times 3. So we have here the 1 minus 0.03, and then 0.1 times 0.2 is 0.04, and then don't forget there's a 2, there's a minus 2, so minus 0.04. 0.2 times 0.2 is 0.04, divided by 2 becomes 0.02, and we're subtracting, so that's minus 0.02. And we say, okay, 3, 4, 2, that's a 0.09. 1 minus 0.09 is also known as 0.91. And that's our approximation. And it's a nice 2-digit decimal value. No rounding, we never round it. And okay, there we go. Well, okay. It is an interesting number. Yes, but for us, we need to keep going. Number 4. Shade the domain of the function f defined by, here we have f of xy is root of xy log of 1 minus x squared minus y squared. We need to use the xy plane provided below. Use solid lines to indicate where the boundary is included and dashed lines to indicate where the boundary is excluded. Also use a small unshaded circle to exclude an isolated point. Okay, will there be an isolated point? I suspect there might be. Now, when we're talking about domain, we usually say we try to avoid our problems. So we see a square root, we know we need to avoid square roots of negatives. So whenever we see a square root, what's on the inside has to be greater than or equal to 0. That says we need that xy has to be greater than or equal to 0. And if you think about what that translates into, it means when you multiply x and y together, you have to end up with a non-zero thing. Well, that can happen if both x and y are positive. It can happen if both x and y are negative. It can also happen if either one is 0. So that puts us into the first and third quadrants. Okay, so just the square root of xy tells us our domain has to only be there for just that one problem. But there's other problems. Okay, we see a log. We know that the log has to be something which is positive. Well, that tells us we need 1 minus x squared minus y squared to be positive. Or x squared plus y squared has to be less than 1. Now, that would be a circle of radius 1. It's a strict inequality, so it's a dotted circle. And we're less than 1, so we are on the inside. All right, so inside. Okay, good. Now, one last thing. We see there's a division going on here. And when we divide, we cannot have a division by 0. That's our problem. Well, when would log of 1 minus x squared minus y squared be 0? Well, that's if we had log of 1, because log of 1 is 0. So what really we need is that 1 minus x squared minus y squared cannot be 1, because otherwise we're dividing by 0. Well, that's the same as saying x squared plus y squared cannot be 0. Well, when does x squared plus y squared equal 0? There's not a lot of points where if I square something and I square something else and I add them together, I'm getting 0 out. In fact, there's only one time that can happen. So the only issue here would be at the origin. So the origin is bad because then we'd have a division by 0 problem, but everything else is okay. So we say, all right, so what do we have? We have sort of these three things. Say, all right, we've got those three things. We just need to make sure we avoid those. So let's put it all together. We know the origin is out, so we're going to put a little circle there. We have to be in the first and third quadrants, but also inside the unit circle. And we're going to include the axes here going out, but not include the unit circle. And I'm going to just I don't really need to, but I'm just going to emphasize the not including itness of it all. And there we go. And I drew extra dotted lines, which I don't need, because we are only going into the first and the third quadrant. That's okay. They'll know what I mean, because the dotted lines means I'm not including it anyways. All right, and well, there you go. Okay, there's our domain. It's kind of a fun picture. Part B. Let f be the function defined by x over x minus y squared if x is not y squared, 1 if x equals y squared. All right, now it says sketch the level curve corresponding to the value or height z equals -1 on the xy plane provided below. So what does it mean to do a level curve? Well, it says you set f of xy equal to -1. Well, certainly that can't be 1, so that's good to keep in mind. So we say, okay, well, suppose we look then at x over x minus y squared equals -1. What does that look like? What's that curve? Well, that's x equals minus x minus y squared, or you could say that's really -x plus y squared, or that's 2x equals y squared, or x equals a half y squared. And I might say, okay, what does a half y squared look like? Now, you might say, I know how to graph y equals a half x squared, so how does one graph x equals a half y squared? Well, you're basically just turning it. So it's going to be a parabola going out to the side. And it's a little bit more shallow, and so we can say, for instance, when you plug in y equals 1, you only add a half. Okay, so y is plus or minus 1. X is at a half. You say y is at 2. X is at, well, if y is at 2 or -2, then x is at 2. Okay, so we have those points. And okay, so we have, for right now, I'm going to just put a dotted line here because I want to talk about something. And now the question here I have is this parabola, do we include everything? And if we don't, what do we need to be worried about? Well, there's a slight issue we might have to be worried about. Namely, do we ever overlap anything that's on the x equals y squared? Because if we do, wherever we overlap x equals y squared, well, that would correspond to where the value of the function is 1 and not -1. So we want to kind of make sure we avoid that. And if we do hit anything, we have to say, well, that point is not in our level curve. So how do those curves relate? How does x equal y squared relate to x equals a half y squared? Well, x equals y squared is a similar parabola, just drawn a little bit more steeply, if you will. But it does overlap at the origin. Okay, so what does that mean? It means that this point at 0, 0, if you plug it into your function, you get 1, not -1. But the rest of the points on this parabola, they're in. And so we now can draw in that solid line. So it's a parabola on its side, but throw out the origin 0, 0. So we'll make it really explicit for our grader. Not at 0, 0. All right, and there we go. Okay, well, we've channeled our inner artistic expression. We're ready to move to number 5. Let g be a smooth function of 3 variables, and let f be the 2-variable function defined by f of xy equals g of xy, x plus y, x minus y. Given that the gradient of g of 2, 3, 1 is 1, 2, 2, find the gradient of f at 2, 1. All right. Well, so let's think about this. So what is the gradient of f? Well, we'll see here that gradient of f, it depends on like 3 slots. And now we have to give names for these slots. And it's a little bit awkward here. So I'm going to think of g. I'm going to call it a function of s, t, and u. I don't want to use x and y again because I don't want to mix too many variables up, because that can lead to more confusion. So s, t, and u, or classic stew. Disco stew, right? Yeah. All right, so we've got our s, t, and u. So what's going on here? Well, we are trying to understand, how does the function depend on x and y? So we say, okay, if I want to get a handle on this, I would say the following. If I want f sub x of xy, right? Because that's the gradient. It's the partial derivatives. Well, I can see there's an x that shows up in the slots. So it'd be g of the first slot, and then times the derivative of the first slot with respect to x, which is y, plus g of the second slot times the derivative of the second slot with respect to x, which is 1, plus g the third slot times the derivative of the third slot with respect to x, which is 1. Okay, so what's going on here? It's a chain rule. G depends on our 3 variables, s, t, and u, and s depends on x and y, t depends on x and y, and u depends on x and y. So we're following it down. G sub s, and then s sub x. But derivative of s with respect to x is y. G sub t, t sub x. Derivative of t with respect to x is 1. G sub u, u sub x. All right, we'll come back to that in a second. Similar, f sub y, well, follow it down. G sub s times s sub y. Derivative of s with respect to y, so we're thinking s is x times y, t is x plus y, u is x minus y. So derivative of s with respect to y is x. And then we have g sub t. Derivative of t with respect to y is 1. And then we have g sub u. And then we say, okay, derivative of u with respect to y is minus 1. All right, now we're almost there. Let's make a couple of observations. At x equals 2, y equals 1, because that's where we're plugging in for x and y, we have that s is 2 times 1, t is 2 plus 1, and u is 2 minus 1. So what's happening is we say, oh, if I want to plug in x equals 2, y equals 1, it's like plugging in 2 and 3 and 1 into g. Very convenient. So here's what we have. F sub x at the point 2, 1. Well, it's going to be g sub s at the point 2, 3, 1. And in case we need it, and I think we do, let's be extra cautious here. So the gradient of g, 2, 3, 1, is g sub s at 2, 3, 1, comma, g sub t at 2, 3, 1, comma, g sub u at 2, 3, 1. So when we're reading this off, we say, oh, g sub s at 2, 3, 1, we can find that out. And all right, we'll do that in a second here. 2, 3, 1. I'm going to just do a little bit longhand. Times y, which is 1, plus g sub t at 2, 3, 1, times 1, which is redundant, plus g sub u at 2, 3, 1. Well, g sub s at 2, 3, 1 is 1, plus g sub t is 2, g sub u is 2, 1 plus 2 makes 5. F sub y at 2, 1. All right, that's g sub s of 2, 3, 1 times x, which is times 2, plus g sub t at 2, 3, 1, minus g sub u at 2, 3, 1. Okay, so that is 1 times 2 plus g sub 2, which is 2, minus g sub u, which is 2. So it's 2 plus 2 minus 2, also known as 2. So what's our answer? Well, we found our partial derivatives, and therefore our answer for the gradient of f at 2, 1, it's our partial derivatives 5, 2. And there we go. There we go. Okay, so this is a chain rule problem. As chain rules problems go, it's not too bad, and it makes sense. You have to sort of say, what's the relationships going on? How do the variables relate? And then once you understand how the variables relate, you say, oh, they're actually feeding us information about certain partial derivatives, and it's the partial derivatives that are showing up in our chain rule computation. Huh, what a fun problem. But that's not our last problem. This is our last problem. Use the method of Lagrange multipliers to find the maximum value of x minus 2y plus 5z on the sphere x squared plus y squared plus z squared equals 30. Your answer should include the maximum value and the point or points at which that maximum value is obtained. Now, we know we're going to use the method of Lagrange multipliers because it told us to use the method of Lagrange multipliers. There are some sort of geometric arguments we can make that might be easier. However, we're not going to do that. We're going to do what we're told because we like our points. We're going to get our points. We work hard for our points. We're getting our points. So, what's our plan? Well, we know what we're trying to optimize because it tells us we're trying to optimize x minus 2y plus 5z. We know our constraint because we can see there's an equation involving x, y, and z equals a number. So that's your constraint. You say, okay, constraint, that's your x squared plus y squared plus z squared equals 30. Now, in terms of what these things mean, so this part right here, this is your f of x, y, z. And then this, x squared plus y squared plus z squared, that's your g of x, y, z. We say, all right, now we have our f and our g, and we say, okay, so what's the plan? Well, the plan is we need more information about how the variables relate. So the constraint right now is saying it's going over the whole sphere. We don't want that. We want to really narrow it down. And we're going to get that. The method of Lagrange multiplier says find the gradient of f set equal to lambda gradient of g and extract information. So this is going to set up, in our case, 3 equations. F sub x equals lambda g sub x. F sub y equals lambda g sub y. F sub z equals lambda g sub z. Okay, so now we'll just work them through. F sub x is 1. That equals lambda g sub x, 2x. F sub y is minus 2. That has to equal lambda g sub y, 2y. F sub z, 5. That has to equal lambda times g sub z, 2z. Okay, so there's a bunch of equations. Now, we're trying to get relationships between x, y, and z. We don't really care about lambda. And so one of the things is if you don't see an easy result or a nice consequence right away, solve for lambda. When in doubt, solve for lambda. That'll get you surprisingly far when it comes to Lagrange multiplier problems. So let's do that. Lambda, well, it's 1 over 2x, but it's also, here if you divide, the 2's actually cancel, negative 1 over y, but it's also, if you divide, you get 5 over 2z. Okay, so now we have some relationships. So let's take a look at them. Suppose we compare the first and the second here. And we'll do some cross multiplying because who likes fractions? Not a lot of people. And if we do that, we get the following. We get that y equals minus 2x. Okay, that's very useful information. Essentially, it says we can get rid of y and replace it with x. That's going to be useful. It turns it from like a three-dimensional problem into like a two-dimensional problem. But we're not done yet. I think we can do more. So for instance, suppose we compare the first and the third. 1 over 2x equals 5 over 2z. Let's cross multiply. That says 2z equals 10x. Divide. That says z equals 5x. Okay, so I can replace z by x. So notice, I can replace y by x, I can replace z by x, and I also have that x as x. So I now don't have to worry about 3 variables, I just have to worry about 1 variable. That's the right number of variables. I like it to be 1 variable, because that's the kind of number that I can use to solve. All right, well, so what do we have here? Let's update. We're going to go to our constraint. X squared plus y squared plus z squared equals 30. But now we're going to use this information here. And we're going to say, well, x, we're not doing anything with that, but y is negative 2x. We're going to replace that. And z is positive 5x, and we're going to replace that. Okay, so that becomes x squared plus 4x squared plus 25x squared equals 30. Well, 1 plus 4 plus 25 gives us altogether that there's 30x squared equals 30. Or x squared is 1. Now, if x squared is 1, that tells us something. It tells us that x is either plus or minus 1. Okay, so what happens if x is 1? Well, if x is 1, y is minus 2 times 1, so you get y is minus 2. Z is 5 times 1, so you get z equals 5. So there's the point 1 minus 2, 5. If x equals minus 1, well, okay, y is minus 2 times x, so y is plus 2. Z is 5 times x, so z is minus 5. So that gives us minus 1, positive 2, minus 5. Okay, so Lagrange multiplier problem, we ran the procedure, we found 2 candidate points. These are on our list, and that's it. There's nothing else on our list. Like, this is wonderful. It's a wonderfully short list. We like this list. Okay, so now that we have this list that we really like, we're almost done. So let's recall what we're looking for. We are trying to find the maximum value of this function, and we need to say where it's obtained. We've now said we only need to look at 2 points. It's these 2 points right here. And so we can squeeze it in. We'll put some work up here. You say, okay, so we're going to plug both of these points, 1, minus 2, 5, and now let's plug that in. That would be 1 plus 4, because minus 2 times minus 2 is plus 4, plus 5 times 5 makes 25, which makes 30. On the other hand, f of minus 1, positive 2 minus 5 would be minus 1. Minus 2 times 2 makes minus 4. 5 times negative 5 makes minus 25, which is minus 30. And we look at that and say, okay, we had our list, we plugged them in, and we say, which one's the biggest one on the list? 30 is bigger than minus 30. So, absolute max is 30 at our point 1, minus 2, 5, and that's the answer to that problem. That brings us to the end. We did it. We did it. Okay, so quick recap of Lagrange multiplier problems. Make sure you know what it is. There's usually, they tell you Lagrange multiplier. But you have a function you're trying to optimize and a constraint. Identify them. Gradient of f equals lambda gradient of g. You're looking to get relationships between your variables. Once you have those, plug those relationships back into your constraint to get points. Make a list. Plug the points in the list and look at your numbers. And there we go. We reached the end. Drop the pen. Life is good. Practice, right? Keep your practice up. The more you practice and the more regular your practice is, so don't try to like cram a bunch of studying into the night before the test. Spread it out and take your time. Enjoy the study. Enjoy the learn. Okay, hope to see you again.